Okay, sorry. I realized after the fact my video got cut off here. So, um, okay. So the series looks, or the sequence looks like the terms are going to be getting smaller and smaller. Like if we put in one more, we're at 1, 2, 3, 4. If we put in 5, we're at 25 over 31. Right? 2 to the 5th. No, yeah. Oh, 25 over 31. So actually we are approaching a value less than 1, right? I think I said before, is this not going to get down to 1? So if we think about this, if we keep going, 36 over 63. Okay, this is definitely decreasing. There's no way that these are going to start climbing back up. Okay, so we can say without having to prove for a lot of these that yes, this is a monotonic sequence. And I probably could have done the same thing here. If I would have written out some more terms, I might have reached sort of enough terms that I was convinced that it was increasing. Now this looks like it's decreasing. So we want to look at, is there a floor? Is there a lower bound? Well, if I'm figuring out the lower bounds, basically I can look at this and say, okay, I know it can't be negative because n squared is always positive and 2 to the n minus 1 will always be something positive as well because 2 to the n won't be 1 as long as n is greater than 0. So I know that at the very least there's a lower bound of 0. But I can do a little better than that if I just take the limit. So if I look at the limit as n approaches infinity of n squared over 2 to the n minus 1. Now, with function races, I know that this is going to come out to 0 because the 2 to the n will grow much more quickly than the n squared. Also, after a couple rounds of derivatives, n squared, L'Hopital's rule, n squared is going to become just 2 over 2 to the n times some series of natural logs to a power. So I know that this is going to come out to 0. So that is the lower bound. These terms are going to keep decreasing without actually hitting 0. Since this is monotonic and bounded, the sequence, C sub n converges. In finding our lower bound, that also tells us what it converges to. All right, so the bound thing is kind of weird because it's like, why are we even bothering with this? But remember, in part A, a sequence can be bounded, but it can still diverge because just because it has bounds doesn't mean that it's always increasing or decreasing to a certain value. So that's why we check both. All right, 1 over n. So we know this one, right? I wouldn't use my monotonic and bounded theorem if I were just asked, does this converge or diverge? I know that this is going to come out to 0. 1 over infinity is 0. So yes, d sub n converges. But we can check it. Is 1 over n monotonic? Let's just check this one mentally. Is it monotonic? Yes. As you start plugging in 1, 2, 3, 4, this fraction is getting smaller and smaller and smaller and smaller. It's definitely always decreasing. So yep, monotonic. And is it bounded? Yes, it's bounded in the fact that it's never going to get lower since it's decreasing, never going to get lower than 0. All right, what about our last one? Negative 1 to the n. This is kind of like A, right? When n is 1, we get negative 1. When n is 2, we get 1. Negative 1, 1. Negative 1, 1. Alternating sequences can converge as long as they are approaching 0. Remember, we have that rule that says, well, if the limit as n approaches infinity of the absolute value of your sequence, your alternating sequence, if that equals 0, then the whole thing converges, the alternating one converges. But if that doesn't equal 0, this is just saying the limit as n approaches infinity of 1, basically, if you take the absolute value of this, that's equal to 1, which is not equal to 0. So E sub n diverges. You can tell that just by writing out the terms, though. They bounce back and forth between negative 1 and 1. They don't approach one single numerical value. All right, that's it for today. We're working on assignment number 10, and tomorrow we'll get into 9.2.